Hello and welcome, dear friends. Today we will discuss about the linear regression models, how we can use that for the financial market problems. So that's what we have named is case studies linear regression models, where we will discuss the bivariate regression, multivariate regression, diagnostic tests, and what conclusion we can get from the results. So you might recall here the basically what we'll do, analyze the Indian financial market using the linear regression model, then they explore the relationship between the financial variables and the market factors. Here we will be using the bivariate and the multivariate regression models, which we have discussed in the theoretical lectures. So we will be using those concepts here to analyze the relationship here. So here quickly I am revising the bivariate relationship. So examine the relationship between Nifty 50 index returns and the crude oil price returns, and we will be using this particular regression form which already we have discussed in detail in the theoretical lectures. So here the idea is basically to get the estimated value of beta 0, beta 1, and that will basically reflect that the beta 0 is nothing but the intercept, and the beta 1 sensitivity of Nifty 50 returns to crude oil price returns. That means if there is a change in the crude oil price return, how it is going, what will be the change into the Nifty 50 returns. That's what I'm going to discuss here. Then in the based on that we'll also discuss the this residual analysis, that it will be checking about homoscedasticity, and we'll also test the heteroskedasticity and the autocorrelation problem. Then in the second case study, we'll be taking up about the multivariate regression model, where we'll be using the price returns, oil price returns, exchange rate, and interest rate on the Nifty 50 returns. Then again here we'll be estimating these three parameters. We'll be also checking about the R square adjusted R square. Then we'll check for the multicollinearity. We'll also check for heteroskedasticity and autocorrelation problems. So these are the things basically we'll be talking about here. So let us go to the R studio here. So as we have discussed in the previous lectures, we have a project folder. Then we'll open it here. So once you click on this project folder, this will open the R studio, and in the R studio we will be having the different files and these programs. Now let me first discuss what is R project and what is the benefit we have. Basically R project here, R project is nothing but, you may recall from your school days, where when you used to get some project, for example craft or something, so we used to make a folder, and we used to make a project folder, the plastic kind of thing, and in that we used to keep all the ingredients needed for that particular project. For example, pencils, color pencils, sketch pen, the papers, the decorative items, erasers, everything. Similarly in our project, basically what we are doing here, we are creating a folder. So in our project we are creating a folder here. So create this folder, in which what will have all the inputs, that is data. We can have the script file, we can have the plots, or even we can have the outputs. So everything will keep in this folder. So that's basically what we mean by the R project folder. And it is a very suggested and recommended way to complete any project. For example, here we have performed the weekly task. For all those weekly tasks, it's better to create a folder, name that particular folder, and perform all those needed in that week in that particular folder. So let us see how we can create that. So to create that, so what we do basically here you can have locate this option, create a project, either from this symbol or we can go from new. Here this we have the new project. So I am showing you either you can take this method or you click here. So both basically follows the similar approach here. So let us click it here. So once you click here, you can see it is showing that it is opening a new project. Now here we have the option. So this version control is for the advanced users, where basically you can keep tracking of whenever you have changed your models is a script file. So that I am not going to discuss here. So here these are the two: new directory and existing directory. New directory, if you have already new directory when you have not created the folder, then we'll keep go there. Existing directory, that means the folder is already created and you wanted to link your project folder to that particular created folder. So already, so let us go to the new folder here. So new directory, then new directory, then there are the different options we have for project. So here we are concerned about the new project. So click on the new project. So here the directory name, or you can browse here. So let us say directory name, here we are having week 3 and 4 case studies. So that's what we have kept the name of this folder. Now where we'll keep that? So pause. Let us say just for this moment I'm keeping on the desktop. So now open. Now here you have the option open new session. So let us click it here and create a project. So a new project folder has opened up here. So now you can see here in this folder here, see users HP desktop and week 3-4. In this folder we have only this project file, nothing is there. So let us go back and first take all those files into this particular folder here. So for that, let us go to the our earlier folder here. So this, so what, so these are the things, this script file and this data file I wanted to take. So let us copy it from here and let us go to the desktop here. In the desktop here I have created that folder. So let us paste those required data and R script file here. Now let us go to our folder here. So now you can see here we have those file. So let us close the old R project. So here we have, now we can see here this we have created here. Now let us go back this folder. So now you can see here all this data file as well as the case study is here. Another advantage of creating our project is that once it is there, directly we can import the data into the R file here. Just click it here, then here we have the option import. Now let us start with the R script, which already we have discussed here. So this is the script file we have. In the script file, everything will be here, the listed, all those programs we have written. Now we have to execute this. Once we open the script file, and then here we'll get a message here with this, there are the certain packages which are being used into this R script file, but it is not installed into this particular machine. So here we can get the option install. So it will install all those packages which is not installed and it is being used in this particular script file. So once we click, automatically it will install all those required packages here. Now see, all the packages has been installed. Then what we have to do? We have to attach that using the function library here. So either we can keep the cursor here and run, or we can select all and run here. So then all of that will be installed. Now these red texts are basically warning messages. It is nothing going to do harm in our case here. Now once we have done, now the first thing what we need, we have to import the data. So to import the data here, now data 1 is the basically, once we are importing that, the data frame's name we are keeping data 1, and this is the read xls. X is the command to import the file with the extension of xlsx. Now we don't have to give the path. Why we don't have to give the path? Because that is in the folder itself. So this is another advantage we have creating a folder. So in that case only I have to give the name of that file along with the extension. So once we have done, then let's import the data. So we have imported the data, then you can see here the environment, the project, an object has been created with the data1 name, because we have to create a data1. Now let us understand the data here. First thing, we imported the data. So logically for anything has to be, you first look out the data. So to view the imported data, what we will be using? You will be using the command view, where the V should be capital, because R is the very case sensitive. Case sensitive means if the command is started with the capital letter, we have to write the capital letter. So V is here capital, so view. Now once we click here, then we can see up here that what we have the 5 variables, that is date, oil price, Nifty 50, USD INR exchange rate, and wholesale price index. So these are the variables we have. So here you can see the 228 observations and 5 variables. This information is also here. So now we have this. So all the data is listed here. We can have a look here. Now next move to the second. Now we can check here the first few observations of the top of the data and the first few observations of the at the end of the data. For that what we use the function head and tail. Then in the parenthesis we write the data frame's name here. So let us execute this. So here we can see the option here. So we can see here that this data has been uploaded. So here we can see these are the date, oil price observations, Nifty 50 exchange rate, and the wholesale price index we have. Once we calculate that, then what we are checking, is there any missing number? If there is any missing number, it will list it out. If there is no missing number, it will give the true and false. Logical answer will be there. If it is false, that means there is no missing number. If it is true, that means there is the missing number. So let us run here. Now here we have seen that we are getting false, false, false. That means there is no missing number. But what you can observe here, we get a long list of these answers. So it is better than, instead of doing that, what we can do, we can use the summary function. Within the summary function, what we can use is NA, then data 1. Now if we execute it here, we'll get an answer here logical in total. So what it is say, date logical false 228. Total observation, how many we have? We have the total observation of 228. Here you can see we have the 228 observations. So we can say all are false. Similarly in oil prices, all are false. Nifty 50, all are false. Exchange rate, all are false. That means there is no missing number. If any missing number would have been there, then it will be false this much and true this much. So here we don't have. Now let's take the summary statistics of the data here. So when we use the summary, which is the basic function, we don't have to use any package here. So we can get the minimum, first quile, median, mean, third quile, maximum. These are the, for every observation, every variable will get this. However, let us say if I wanted to more descriptive statistics detail, then we'll use the package psych, and from that package we use the function describe. So let us say we are using the describe, then here we can see here that mean, because this is the date. So obviously for the date we don't have any information, so we will not be using that date. So we will have oil price, we have for Nifty 50 exchange rate and wholesale price index, we have all these informations here. Mean, standard deviation, median, trimmed mean. Trimmed means removing some outliers at the top and at the bottom of the data. And here mean absolute deviation, minimum, maximum. Then we have also skewness, range, skewness, kurtosis, and standard error. So these are the detailed information we'll get. Because of the date, we are getting these errors. So let us do away with that. Here, describe. Now we know that in the data function 1, but here what we have, the first column we have the date. So we can ask that kindly find the descriptive statistics -1, that is the delete the first column. So now let us run here. So now you can see there is no warning, and we have only for oil price, Nifty 50 exchange rate and wholesale price index. So no more descriptive statistics of data. Now what is the structure of data? So if we click here, then we'll got, okay, it is a table. That means it is a data frame that where the column and we have rows. So in the column wise we have observations, the row wise we have the number of observations. So class of the data, we can say here the class of data is either table, data frame, table, or data frame. All three is the basically similar kind of representation of the data. So all those we talked about the data. Now we can, if you think, we can plot the data also. Let us say if you are plotting the data, so here I will plot the individual series here. So data 1, then using the assessor sign I'm asking to plot the oil price. So here we can see the oil price. So it is showing this. So we can line LTY is equal to 1. So here we can see the plot of this data. Similarly, we can plot the other variables. Now let us take the first case study, that is we wanted to find out the relationship between the Nifty 50 and the oil price. For that what we use the function LM, that is the linear regression model here. Basically LM is the linear model is the package, and from that lot of different options we have. Here we are using the linear regression model. So first reference we are giving data, that is data is equal to data 1. So that means we are asking R to look the data in the data frame data 1. Now here what we can observe, data 1 and Nifty 50, that is the about the first observation, the dependent variable. Then what we have, it is known as the tilde. So which will be located on just below the escape button in your keyboard, and we have to use shift and press that button. You will get this symbol tilde here. So just remember, just below the escape button we have a button in which here we will have apostrophe comma and this tilde. So to use the tilde, what we have to use the shift plus press that particular key here. So here the Nifty 50 is the dependent variable, then tilde regressed upon the independent variable, that is the oil price. So let us take here this. Now let us take the summary data here. So we can observe here the Nifty 50 does not depend on this oil prices because it is not significant here. You can see the p value is 0.89. That means we are accepting the null, where the null is so here what we have the regression equation y is equal to alpha plus beta x plus u. Then we have estimated, so we get alpha hat plus beta hat x. Now whether this is the significant or not, we use the t statistics, or respectively the corresponding value is p value. So here the null hypothesis is that beta is equal to 0, and alternate hypothesis is beta is not equal to 0. Now if based on the t statistics or corresponding p value, what we can have, if the t statistics, calculated t statistics, is more than tabulated t statistics, then we reject the null. That means no, the value of beta hat is statistically different from 0. However, the similar decision we can take based on the p value. So if the p value is closer to 1, that means we accept the null. That means the value of beta hat is equal to 0. However, if the p value is closer to 0, then we reject the null. So that means beta hat is statistically different from 0. So that's why we are going to use it here. So we can observe here this estimated value, this is standard, the t value, and here the probability. So it is close to 0, therefore it is significant here. It is close to 1, that is there is insignificant. What does it mean? It means the oil price does not have a significant impact on the Nifty 50 returns. However, let's check the diagnosis statistics for that. So if we are taking the diagnosis, first we will take the residual. So we are extracting the residual using the command rigid and giving the reference of the model, and we are storing that into this here residual. Now if we here see, these are the basically residuals we have. Here see, we can say we have stored the residuals. Now let us plot that residuals here. So this is the residual plot we have. It seems there is no significant effect. So as the time passes, the residual is also increasing because the coefficient is not significant. Then we can also test for the heteroskedasticity using the BP test, that is the Bruce-Spagin test for taking the heteroskedasticity or normality into the data. So here what we are having here, here the null hypothesis in the Bruce-Spagin test is that there is no problem of heteroskedasticity. However, here you can say the p value is closer to 0. That means we are rejecting the null hypothesis. It means there is the problem of heteroskedasticity. Similarly, we can take for the problem of autocorrelation. So let us check the problem of autocorrelation. So here in the autocorrelation, we are using the DW, that is Durbin-Watson test statistics. So what basically we are using here? In the Durbin-Watson statistics, test statistics for autocorrelation. For this, what we know, there is the two upper limit and lower limit we have, but we have the rule of thumb based on that what we have observed. If DWT status is around 0, that means there is no autocorrelation. If the DW is closer to 0, that means there is negative autocorrelation. if the Durbin-Watson statistics is closer to 4, that means there is the positive autocorrelation. So this thing we have discussed into the theoretical discussions. Now if we observe here, in this case what we have, here you can observe the Durbin-Watson statistic 0.9744, that means there seems the presence of negative positive autocorrelation. Now that means we have the problem, this model is not perfectly fit. So let us make some changes here. We know that to remove the autocorrelation, what we have to do, we have to include the lag terms of the dependent variable, because the autocorrelation means this year's error term depends on the previous year. That means on the previous observations of the dependent variable. So for that, what we have done, we have to corrected the model by including the lag of the Nifty 50 here. Now let us run here. Enter, then let us check the summary here, summary statistics. So if you are taking the summary statistics here, so what we can observe here, again this oil price is not as significant, however the lag and the intercept is significant. But here we have to be little bit careful about this result. Why we have to careful about this result? Here we are getting adjusted R square is equal to 1. That means this model is perfectly able to explain the variation, which is a doubtful problem we have. So in such cases we do not have a reliable estimate. So while doing this we have to be very careful about this result here. So here that's what we are getting a warning message here. Now let us see here. However, we have the corrected model. So let us now check the heteroskedasticity test here. Now here we can see the heteroskedasticity test, the p-value is 0.45. That means in the heteroskedasticity test what we have, we null have, there is no heteroskedasticity. Now we have the p-value is around 0.4, that means closer to 1, so we can accept this null. That means we are accepting that there is no problem of heteroskedasticity, or in other sense we can say that it is satisfying the assumption of homoskedasticity. Now let us take the problem of autocorrelation. So here we are using the problem of autocorrelation. Then here we can observe this here, that what we have the lag of autocorrelation, that is Durbin-Watson statistic, the 2, the p-value is 0.3. Then again, what is the null here? We have null for the Durbin DW statistics is coming, this is around 2, so that means null here, there is no autocorrelation. Again the p-value is closer to 1, so we are accepting the null, and we can observe that we are basically satisfying the assumption of no autocorrelation. However, one thing we have to remember, what was the problem limitation of the Durbin-Watson statistic? The DW test has the limitation that if you include lagged values as regressor, then we cannot use DW test, and here we have included lag of the Nifty 50. So in that case what we have the alternative of what we known as the Durbin H test. So basically here we are performing this Durbin H test, which has been modified to be used when we include the dependent variable as a regression into the regression model here. Now, so this is the case of the bivariate regression model we have, and here we have seen it is not perfectly fitting. There is the problem, and that's basically the as per the expectation of from the finance theory. Why finance? Because the stock return does not depend only on the oil price. There are the many other factors on which it depends. And if you are not including those, then obviously we will not get any better good estimate of those models. Basically we are ignoring lot of significant variables, and this model is misspecified, and we have the issues of autocorrelation, other non-normality and other things, and it is the coefficient is not also significant. Now let us, therefore we have to include all those variables. If we are including those variables, because it's a complex relationship where the Nifty does not depend only on the oil price, there are the many other factors which could have an effect on the return of the Nifty 50. So that's why what we are going to do now, we are going to use the multiple linear regression model. In that case here, now model 2, the same function we are using the LM, the data is the, here we are giving the same data 1, only thing now we have added, now this data 1 Nifty 50 is the dependent variable before the tile. Now we are including this oil price plus the another variable, that is exchange rate, plus another variable, that is inflation here. Now let us execute this. So to add the other variables, so to add the multiple variables in the normal linear regression model, what we have, y is equal to beta 0, beta 1 x plus beta 2 x2 plus let us say u. So to include the multiple variables, what we do in the R, that we use the same LM function for the linear models. Then we give the reference of the data where we have the data. For example, in this case, our data frame name is data 1, then comma. Then what we are doing, then the dependent variable. So dependent variable we have Nifty 50. Then we have tiled symbol. So this is the dependent variable. After the tile, every other variables will be treated as the independent variables or the regressor. Then what we have, we are including oil price, then add another variable by giving the symbol plus, the plus sign will use, then we have the exchange rate, then plus inflation, then the parenthesis closed. So that's how we have incorporated the multiple linear regression model into R. So that's what we have done here in this case here. Now let us run this. Let us take the summary statistics here of this. So you can see the summary statistics: intercept, it is significant, oil price is now significant, exchange rate is not significant, and the inflation is also significant. Now remember, due to the misspecification in the previous equation, though we have included only oil price, but it was not significant. However, now it is showing the significant. And the coefficient is minus 26.99, which basically shows the real economic phenomena. Okay, when there is the increase in the oil prices, obviously inflation will increase, the prices will increase, and there will be the negative expectation of the return of the assets. So Nifty 50 may go down, and that's basically it is showing here. Now check the other things. So these are what we have observed. Except the exchange rate, all other variables are significant. Another thing now what we are observing, this multiple R square is 0.864. Here the adjusted R square is 0.863. Again, if you remember here what we have talked, that adjusted R square cannot be more than the R square. So here we have 0.8648, here we have 0.863. So r square will be always more than the adjusted r square. Another thing what we have discussed in theoretical class, if the number of observations is large enough, then there will not be much difference between the r square into the and adjusted r square, and which is basically true here because the number of observations we have 228. Then the F statistics, here the F statistics basically says the overall significance of this model. So here we are using the T statistics, the T value for the to test the individual significance of the coefficients, and if we use the F statistics to examine the overall significance, that it simultaneously all the coefficient is not equal to 0, which is basically true here. Now the next task what we have, to estimate the diagnostic test here. So first diagnostic test, we are using the variance inflation factor to find out whether there is the error problem of multicollinearity do we have. So let us first check this. So we have used the VIF, then the estimated model reference we have given, and now let us see what is the value of this. Now here you can see the VIF value here. Now what we can observe, the VIF for the oil price is 2, that's less than 10, so there is no problem of that. However, in case of exchange rate and the wholesale price, we do have VIF more than 10, that means there is the problem of multicollinearity. And theoretically it is obvious. The prices do get reflected into exchange rate. So if the price is moving upward, the exchange rate is also moving upward. So that's from the theory, economic theory of purchasing power parity, or we have. So this shows that there is the problem of multicollinearity among these. Now let us take the other test, that is the Bruce-Pagan test for heteroskedasticity. So we are having here. So again here you can see what we have. P value is closer to 0, that means we are rejecting the null, so that is there is the problem of heteroskedasticity. Now similarly we can see here the Durbin-Watson statistics. Now again what we can observe here, it is close to 1, that means there is the problem of positive autocorrelation. That means we have to make some changes into our existing model. So in the existing model we are making the change here. So what is the first change we are making? Okay, that there was the problem of multicollinearity between the exchange rate and wholesale price index. So one way out is to drop one of the variable. So here we have dropped exchange rate because it was not also significant. So let us now run this model. So here we have this. So now you can see here this the coefficient. So all the coefficients are significant. Then what we are seeing here, the residual multiple r square is 0.86, adjusted r square is 0.8635, F statistics. So all three seems good as for now. Now let us check the other diagnostic test. For example, let us check the VIF here. So now you can see the VIF here we have this, which is quite less than 10, that means there is no more problem of multicollinearity. Now let us similarly test as the heteroskedasticity here. So we can observe here heteroskedasticity, the p value is close to 1, so seems there is no problem of heteroskedasticity. Now let us go back to Durbin-Watson statistics here. So here we are having the problem of autocorrelation. If this is the case, then what is the way out? We have to include the lag variable. So if you are adding the lag variable, we can remove the problem of autocorrelation here in this case. So now that's the basically how we can use the linear regression model to estimate the relationship between the financial. Now, what is the inference we get? What inference we can make from this particular case? For that, let us see this particular case here. So, what we can observe? If the oil price is increases, then the return of the Nifty 50 will decrease. On the other hand, if the inflation is increasing, then there will be increase in the return of Nifty 50. So there is a positive relationship between inflation and the Nifty 50 return, while there is the negative relationship between oil price and the Nifty 50. So that's the basically how we conduct the we use the linear regression models to examine the relationship between the financial variable and the market factors. Here we have using and we have implemented those using the R. Thank you so much. We will see you in the next class.